All right, so first thing we're going to talk about is polyatomic ions. How do I write a formula for a substance using polyatomic ions? So what we need to first know is what is a polyatomic. So poly means more than one. Atomic is atoms in a molecule. And then we said ion, which is a charged particle. So every time we say polyatomic ion, we're saying more than one atom in a molecular formula that is in a ion form. It is a charged particle. Okay? So we learned on last week, I gave you 22 of them I wanted you to start working on trying to figure them out. The reason that I do that is because it makes it faster and easier for you to write formulas. And today you're going to learn that writing the correct formula is the most important thing moving forward. If you can't write the correct formula, everything else is going to get messed up. Okay? One of the first things that I try to get you guys to learn were diatomic molecules. I put that out early because I know at this point people will mess it up. So I want you guys to remember all the stuff that you've been learning up till now because it's important to move forward. Okay? So there was one polyatomic ion on that list that I gave you that forms a positive charge. Only one, and that was NH4 with a +1 charge. Anybody remember what that's called? Go ahead. This is ammonium. Outstanding. Ammonium is the only polyatomic cation you guys are ever going to see in this class. So let's make some compounds with it, right? If I have NH4 with +1 charge, and I have chlorine with a -1 charge, because chlorine is in group 7A, forms a -1 charge, it will then, because it's only gaining one electron to get to that octet. My brain is not flowing right now. We'll get this right though. How many do I have to add of each one to make it a neutral compound? They're the same, right? +1, -1. So that ratio is already done for us just because I have +1, -1. So the formula is just NH4Cl. And what would I call this? I would call this ammonium chloride. So I see a formula. The first thing I'm going to say is, does it begin with a metal? If it's yes, I would draw a vertical line right after that metal. And I'll explain why in just a second. If my answer is no, I'm going to ask, does it start with ammonium? In this case, it does. NH4 is ammonium. It starts there. So if I draw my imaginary line, you don't have to actually draw it, but think there's an imaginary line right after the cation. Okay? That's going to dictate everything else. If it starts with a metal, I'm going to draw it right after that metal. If it doesn't start with a metal, I'm going to look, does it start with ammonium? If it's one of those two things, it's an ionic compound. Okay? And that means everything to the left of this line is my cation, and everything to the right of this line is my anion. Since my anion is an element in this case, I just use the same naming rules that we've been using all along for the anion. The root of the anion with the ending IDE. Okay? On the left side, normally I would write just the element name, but this one is not an element, it's a polyatomic ion. Anytime you use a polyatomic ion in an ionic compound, you just write the name as it is. That's it. Period. No, nothing else to it. Am I cool with that? All right. What if I have NH4 +1 with something else like sulfate? Sulfate is SO4 with a -2 charge on this. Which do I have more of, positive or negative? Go ahead. You don't have to raise your hand.
Negative.
I have more negative, so I'm going to add another positive here. Notice that I'm adding the entire polyatomic ion. It takes the whole form to have that charge. I can't separate it. I can't rearrange it. This is not going to become N2H8. It never does that. And I'll show you how it should look in just a second. Do I have more positive or negative now? They're the same. So since they're the same, I have ammonium and I have sulfate. But how many sulfates did I use? There's only one sulfate. So I can leave it just like it is. How many ammoniums did I use? I used 2 of those. So I would put a 2 right there, right? That's right? No, why is that wrong? Now it looks like I have 42 hydrogens in here, and that's definitely not right. So I'm going to put a parenthesis here and here. And now that 2 is applying to everything within this parenthesis. Does that make sense? So if I want to count how many atoms of each element I have, I would say how many nitrogens? Well, there's a 1. There's nothing there, so that means there's 1, right? But I have 2 of them. I have 2 ammoniums. So that 1 becomes 1 times 2 is 2. How many hydrogens do I have? In the polyatomic ion, there's 4. But I have 2 of those polyatomic ions, so 4 times 2 is 8. So there's 2 nitrogens, 4 hydrogens, 1 sulfur, and 4 oxygens. Does that make sense, everybody?
Yeah.
We're all cooking the same chickens? All right. NH4 plus 1 with phosphate, PO4 with a -3. What do you guys think we're going to do here? Now, some of you really love using the crisscross method. You can still use the crisscross method if you remember that it is applying to the whole polyatomic ion. So the crisscross would be this. So this becomes NH4 with 3 behind it and 1 phosphate. You guys cool with that? I thought I had it wide enough where I could see the whole page. Is that Gouda?
Yep.
Mas Gouda, meaning more smoked cheese in Spanish? All right. Why do I need all this? Why is it important that I know how to write all this? Let's write these names here so I can make sure everybody remembers. What is NH4 again? Ammonium. Okay, if I draw my vertical line after ammonium, I have 2 capital letters to the right, which means that has to be a polyatomic ion. I look at my polyatomic ion sheet, or I remember it because it's one of the 22 that I gave you. What is SO4? I have an anion here that's more than 1 letter, so I need to look it up. What is SO4 going to be? Anybody have their ion sheet out? Anybody remember them yet? Not sulfite. It ate 1 more oxygen. What would it be? This one is sulfate. All right, down here, I see NH4, so I'm going to draw my vertical line. Everything to the left is my positive. Everything to the right is my negative. I see I have more than 1 capital letter on the left. I know there's only 1 polyatomic cation, so I'm going to go ahead and write in my ammonium. I also have more than 1 capital letter to the right of that line as my anion. What do I call the polyatomic ion that's PO4? PO4 is what? It is phosphate, exactly. Everybody cool with this? Now, this is how you name polyatomic ions. You just write the name of the polyatomic ion. You don't change anything else. If I'm using a transition metal in there, I use the transition rules as well. If I have a representative metal in there, I use representative rules. Okay. If the cation is a transition metal, in the name, I should see the Roman numeral still. Make sense, everybody? So if I have iron and sulfite, which do I have more of, positive or negative? So I'm going to write another negative in there. Which do I have more of, positive or negative? They're equal now. So this becomes FeSO3, and I have two of them, so I have to put in parentheses. That's the formula for this. How am I going to name this? What is Fe? If you're looking, it's number 26 on your periodic table. This one is iron. Is iron one of my representative metals where I know what charge it's going to make? Is it in group 1A, 2A, or our stealth bomber 6? No, it's not. So what do I need to put in here to demonstrate that it is a transition metal? Roman numeral. What does the Roman numeral have to represent? It's the charge of the cation. So what is the charge of this cation? It's a 4, so I have to put an IV there. And then what is it connected to? What's the anion called? What is SO3 called? This is sulfite. Everybody cool with this so far? Okay. What I'm about to show you is a presentation that I made many moons ago. And I fine-tune some stuff every year. And one of the things that I fine-tuned was that I wanted you guys to use these 4 rules when you're finding the molar mass of a substance. These are the rules for finding molar mass. Okay? If I go a little fast here, guys, remember I'm recording this and it's going up on YouTube. You can come back and check it over and over. So if you're missing notes, you can always go back and look at this again, okay? But our rules are, number 1, you must write the correct formula. Number 2, you must find the mass of each element in the formula. Number 3, you're going to multiply the mass of each element by its subscript. And then number 4, you're going to find the sum of all of the elements in that molecule. That sum will be what's called the molar mass. So what is this molar mass that I'm talking about? Well, we start by talking about moles. Moles are the number of particles of any substance that it takes to equal its atomic mass in grams. So it's a conversion factor. This is a ratio that never changes. It does not matter what the substance is. If I use this number that we're going to find, then I will be able to determine how many particles it took for it to go from atomic mass to grams. Why is that important in this classroom? Do we have any piece of equipment in this classroom that measures moles? No, it does not exist. So in order for us to get to this ratio, because this mole ratio is that thing you guys learned in 7th grade, when you learned how to balance chemical equations by putting those big coefficients in front of the molecules, and then that tells you how many molecules that you need in order to have the same number of atoms of each element on both sides of the equation. Those coefficients are a ratio for a recipe. Once I know exactly how much it takes to balance that equation, that becomes a recipe. Those coefficients are the ratio of moles between those substances. It could be particles. but more often than not, it's the ratio of moles. Does that make sense, everybody? So, what is this big old number that I'm telling you about that you need to know that will help you to understand how many particles it takes for a substance to equal its molar mass, equal its atomic mass in grams? This number is called Avogadro's number. And you're going to get absolutely sick of seeing this number. Okay? And maybe I can even make you sick of hearing it if I play the mole song for you. So, Avogadro's number is based off of how many particles it takes for a substance to equal its atomic mass in grams. It was originally done using carbon 12. They said this is how many particles it takes for carbon 12 to equal 12.01 grams. And then they found out as they ventured out from that, it doesn't matter what the substance is, it will always take the same number of particles to equal its mass in grams. Okay? This number is 6.02 times 10 to the 23rd particles. Okay, I've been saying particles, 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 right? Particle is a big umbrella word that stands for the number of, I'm sorry, I messed that up. Particle is the smallest unit of each substance. So if I'm looking at an element, the smallest unit is an atom. If I'm looking at a diatomic, the smallest unit will be a molecule. If I'm looking at a covalent compound, the smallest unit is a molecule. And now my favorite, if I'm looking at an ionic compound, the smallest unit is called a formula unit, or an FU for short. Now you see why I like it so much? Because my brain still thinks like a 16-year-old sometimes. And that's funny. I don't care who you are. That's funny right there. So how big a number is this Avogadro's number? It's 6.02. If I move the decimal to account for that scientific notation of 10 to the 23rd, since the 23rd is positive, I'm going to move the decimal to the right. So I'm going to say 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23.
It's a lot of zeros.
So this should tell you something. This is a huge number, meaning it takes a lot of particles for a substance to equal its mass. Everybody who has a water bottle, lift up your water bottle right now. Hold your water bottle up in your hand. If that water bottle contains 18 grams of water, it's actually 18.02. If that water bottle has 18.02 grams of water in it, you are currently holding more particles of water than there are stars in the entire universe. That's the truth. Dead honest truth. Okay? Let me give you some references to help you understand how big a number a mole is. I went through college at NIU in DeKalb. That's why I live in DeKalb, because I can't leave there now because I can't sell my house. I went there for college. I went to chemistry in there. What do you guys think that they're going to use as a reference for size of something in DeKalb?
Pounds.
Not pounds. They use, what's that?
Kilo.
They use corn.
Oh yeah.
If I want to represent something, if I wanted to get you to see how big the number something is, I'm going to use corn to tell you what it is. So here's what they taught us. If I have 1 mole of corn kernels, it would cover the entire land surface of Earth with 3 stories of corn kernels. That's a whole lot of corn. Ain't nobody gonna be hungry no more.
It's corn.
And then there's a song came out. There's a former teacher taught up in Barrington High School. I've met him a couple times. I like him. Singing's not that great. His musical talent is not that great, but his creativity in writing a song is freaking amazingly good. Love what he does. Okay, if you got a professional singing it, it would actually sound really good. But I was listening to these songs, and I used to actually have my kids sing the songs. I even have the songbooks down in my office. We could revisit that if you guys ever want to sing. I could bring out the
Rock TV.
I could bring out the songs, and we could sing along to "A Mole Is a Unit" by Michael Offit. But in that song, it kind of gives us some references. His numbers are a little off, but it's still. I actually did the calculation, and it's actually still correct. There are about 7 billion people in this world.
It-
7 billion people in this world. If I had one mole of pennies, if I had this many pennies, and I equally distributed them to every single person on earth, all 7 billion, every single person would get $1 trillion.
Dang.
That's, that's how many there are in there. Okay? If I had a mole of marshmallows, it would cover the surface of Earth with 11 miles of marshmallows. And if every single person on Earth ate one marshmallow every second, it would take 40 million years to get rid of them.
Damn it, diabetes.
We have a whole lot of really, really fat people.
Yeah.
Not good. So this number is a really big number, right? While this number is big, it should give you a little insight of how small these particles are that we're working with. You were holding more particles of water in your hand than there are stars in the universe. But look how little that amount actually is. 18.02 grams of water has this many particles in it. Okay? So we need to know about molar mass. What is molar mass? And I apologize if you guys get a little nauseous, but I love doing it this way. This makes me happy. Our target for today is that you will be able to find and or calculate the molar mass of different types of substances. To find the molar mass of a substance, a chemist will need the correct formula. Remember our rules. Number one rule is to write the correct formula. If you don't have the correct formula, none of this other stuff is going to matter at all. You're not going to get it right. It'd be helpful to have a periodic table, and you actually need the periodic table unless you've got it memorized. And it would be helpful to have a calculator, because some of these get like really big compounds, and you're going to have to measure. Take a lot of them and calculate them all up. Okay. So the molar mass is the mass of 1 mole of a substance. That's how the mass of how many particles it takes to convert its unit of measurement from AMUs to grams. That's that Avogadro's number. That's how many particles it takes to get the mass in grams. Everybody cool with that? All right. When you find the molar mass of an element, this is where I start to diverge away from this. I get away from what I have on this presentation because I went to these 4 rules instead. I was explaining it out a little bit more in detail here than I did on that one, but that one works better because then there's no confusion. Okay? If I'm finding it for an element, I just look it up on the periodic table and change the unit. That's all it is. But if it's a diatomic element has a formula, which we're going to work with that in just a sec. So let's go find one of a simple element. I'm looking for iron. Iron is number 26 on the periodic table. So I go to my handy dandy periodic table, and I see that iron has a mass of 55.845. Everybody with me on this so far? Am I going to use that nowadays? No. But back then, I didn't even think about it, and I used that whole number. Nowadays, what I would say is if I draw a line after the second digit, if the number behind that line is 5 or above, I'm going to raise up the digit to the left by 1. If it's 4 or below, I just drop them off and I leave that as is. Okay? Don't round down. That's a problem that some people have been having the last couple of years, and I don't understand where they're getting that from. You don't. This doesn't change down to 3 if this was a 3. It stays at the 4. If it's 5 or above, it goes up 1. If it's 4 or below, it stays the same. Everybody cool with that? All right. Come back up here, and it says the atomic mass for iron is 55.845 AMU. To show the molar mass, we just change the unit to from AMU to grams. But I'm measuring the mass of 1 mole. That's key. If I'm measuring the mass of 1 mole, the unit is going to be grams per mole. Does everybody understand that? That's a big key that you have to have right. If I ask you what's the molar mass of this substance, and you said it's this many grams, that's wrong. If I ask you for how many grams there are in this many moles, that's only going to be grams. But if I'm asking for the molar mass of a substance, the unit must be grams per mole. Does everybody understand that? I'd write that down somewhere if you haven't done so already. If I'm asking you for the molar mass of a substance, the unit must be in grams per mole. All right. Let's find a diatomic now. I told you before we're going to come back to it. Here we are. Nitrogen is a diatomic molecule. That means in order for nitrogen to be stable, it exists in a molecular form. It has 2 atoms connected together with a covalent bond. Okay, in this case, it has 3. It's a triple bond. So the formula for nitrogen becomes N2. Does that make sense, everybody? That's my correct formula. I found number 1. Number 2, I'm going to find the mass of the nitrogen. I am not writing all those digits down. I'm going to come to my second digit, and I see the one to the right of it is a 6. So since that's a 6, I'm going to round the one previous up by 1. Done, and everything else gets dropped. So this becomes 14.01. That's the mass of the element. So I got the number 2 now. I found the mass of the element in the formula. Next thing it says is to multiply the mass of each element by its subscript. So as I go through this, it comes to the same thing. The mass, 14.01. The subscript is 2. What is the molar mass of nitrogen gas going to be? I'm at number 3 here. I need to multiply the mass of the element times its subscript. So what is 14.01 times 2?
28.02.
28.02 is the molar mass of nitrogen gas. What's my unit going to be? Because I'm asking for molar mass. What's my unit going to be?
Grams per mole.
Grams per mole. Everybody with me on that?
Yeah.
All right, how about a compound? Carbon dioxide. Formula of carbon dioxide is CO2. When I go look them up, carbon, I round this one here. That's a 0, so I'm going to leave it as 12.01. Is everybody cool with that? So I know the mass of carbon is 12.01. Then I come to oxygen, 15.9994. What's this going to round to? 16.00. So I come up here and I say carbon adds 1 times the 12.01. Oxygen adds 2 times the 16. So 12.01 plus 32.00 is going to equal 44.01. That's the molar mass of carbon dioxide. We're all cooking the same chicken? All right. Tonight, you need to study your polyatomic ions. Make sure you get them stuck in your head. Otherwise, tomorrow we're going to do an activity that I've created on molar mass that will help you guys to really, really understand it. And it's a little fun too. So I will see you guys tomorrow. Class isn't over, but